Okay, hello everyone. Welcome to today's lecture. This is the 16th lecture of the course on Cyber-Physical System Fundamentals. In this course I'm teaching Embedded Systems, Foundations of Cyber-Physical Systems, and today we are covering the remaining material of the chapter 5 of this very great companion textbook. That chapter 5 is entitled Evaluation and Validation, and you should remember that evaluation and validation are activities that we do have to perform during these design cycles that also involve application mapping and optimization. In this chapter, we are considering the different criteria by which we have to evaluate the different designs. You should remember that we had this slide already before. I did explain the various objectives that we are considering there on this slide. Today, I will start the lecture by first of all looking at reliability issues. Reliability issues are becoming more and more important because of the impact of shrinking feature sizes for semiconductor devices. We know that due to the shrinking devices or due to the shrinking patterns there in the devices, we have a reduced reliability there for integrated circuits, and we are expecting this reliability to be decreasing even further in the future. As an example, we can see that there will be transient and permanent faults, and we could have, for example, a case of electromigration, where electromigration means that due to the current which is flowing in the circuits, some of the patterns that we have put into these chips will start to kind of melt away. So these solid-state circuits behave a little bit like a pudding, where the pudding is then moving away. So for example, you see over here a case where initially we had a metal wire which has now completely drifted away, and you only see certain fragments there of what initially was a solid aluminum wire. We expect that the rate of faults is increasing in the future, so that designs must become fault tolerant in the future. Non-fault tolerant designs cannot be used in the future. There are many examples of movies that demonstrate how for example, metal migration is occurring in a circuit. You might look around in the internet to find the corresponding movies there. I'm just showing the initial image there for one of the movies. I suggest that. Please stop. So that is just the initial few seconds. I'm not allowed to really show the full video for copyright reasons. So therefore I suggest that you look around for this video and start it yourself. So back to the slides. When we talk about reliability and the different types of problems that we can observe in the system, we have to distinguish between different types of problems that could happen. In particular, I'm going to distinguish between three different types of problems. The first is a problem that is visible at the user level, and we call this type of problem a service failure. A service failure is often abbreviated here as a failure, and such a failure exists in the case when we have a situation where the delivered service of a system is different from the correct service. So that means, for example, we would like to make a phone call, but our mobile is not working. We would like to use a PC, but the PC is not working. From this we distinguish the so-called error. An error is a situation in our system that is not consistent with the correct situation, with the correct state there in the system, but it might not immediately lead to a failure. It might only be the case that inside the system there is something different from the expected situation, from the expected state, but it doesn't mean that there is immediately a service failure. And then from this we distinguish so-called faults, where faults are effects that usually are happening at the physical level, and these faults are the reason why later on we might be observing a error or a failure. Faults can be internal or external of a system. So as an example, I'm considering the three different levels there. In the case where we have a flipping bit there in the memory, there we can have a so-called transient fault, which is flipping a bit in the memory. After this bit flip, the memory cell will be in error. But it may happen that this doesn't mean anything immediately, because possibly we are not even accessing that memory cell. Later on, it can happen that this is indeed leading to a failure, and in this case we would have a failed service. So that means as a user we cannot use the system in the intended way. So in the following we will not be looking at errors, we will just be looking at failure rates. That means at the rates at which the service that we are expecting is not available. And we will be looking at fault models. That means we will be looking at reasons why something later on might be going wrong. Now first of all, we are looking at failures. Now failures are usually modeled in the context of the so-called reliability, which actually is one of the key terms. It's one of the key requirements that we are expecting from cyber-physical and embedded systems. Reliability is defined by first of all referring to a so-called random variable. A random variable, in our case denoted as capital T, is a time that models is a variable that models the time until the first failure. So that means in this context we are referring to some hopefully present previous knowledge in the context of statistics and stochastics. For this random variable, we are introducing f of t as the so-called density function for that random variable. And as an example of some density function, I'm considering the exponential distribution, where the density function is shown on the slide. The density function is equal to lambda times e to the power of minus lambda t. We can visualize that function graphically. You see that we have this exponential decrease there starting from a value of lambda for t equals 0. Now, as we do commonly in statistics, in addition to using the density function, we are also using the probability of a variable to have a certain value. And in this context, we are therefore introducing capital F of t as the probability of a system being faulty at a particular time t. That means this probability is the probability of that random variable capital T to have a value of less than or equal to lowercase t. That means that the first error, the first failure more precisely, happens no later than at time lowercase t. This probability can be computed like what we do frequently in statistics. This probability can be computed by integrating from 0 up to that particular point in time t, and the integral is taken over this density function. We can also demonstrate this for the exponential distribution. For the exponential distribution, we have to integrate this density function, and when we do this integration, there will be a factor of minus lambda that will be propagated into the denominator, and as a result, we will have this expression there for the evaluation of that integral. We will have to consider the bounds 0 and t, and if we insert the bounds 0 and t there, we come to the conclusion that the probability of the system being 40 at time t is 1 minus e to the power of minus lambda t. Again, we can visualize this function graphically. Obviously, we are starting at a value of 0 there, because for t equals 0, this second term is equal to 1. And then as time advances, this probability will also approach 1. That means for very large times t, the probability of the system being 40 will approach 1. Now, in addition to considering the probability density and the probability, we are also introducing formally the term reliability. And formally, the reliability is defined as the property that the first time, or that the time until the first failure is larger than some time t. That means the reliability is defined as the probability of that random variable capital T to be larger than our time t. And that means that, again, we can use integration to find that value. The reliability at time t is just the integral from that time t until infinity over that density function. Now we can add the reliability and the probability of the system being 40 at time t. That means we have to add these two integrals, and in this case we are integrating from 0 to t, and over here we are integrating from t to infinity, which means that we are integrating over the whole domain of our variable that we are considering, and since probabilities are normalized, the sum must be equal to 1. That means if we rewrite this so that we have this reliability on the left-hand side of our equation, we come to the conclusion that the reliability is 1 minus the probability of the system being 40 at time t. And we can differentiate this equation on both sides. And as a result, we come to the conclusion that the probability density is equal to minus the derivative of reliability with respect to time. Again, we can demonstrate this for the exponential distribution. If we do the calculation for the exponential distribution, we can use the special form of the reliability there for that particular distribution. It's e to the power of minus lambda t. And as a result, we can also visualize this function graphically. We see that we are starting at a value of 1 there. And for the case where t equals 1 over lambda, we have e to the power of minus 1, which means that we have this fraction of the reliability that's left of the original reliability there. So in this way, we can demonstrate what it means to compute the reliability for one particular example. Now, in many contexts, it's very important to compute the so-called failure rate, where the failure rate is the failure rate at a particular time is defined as the probability of a system failing between time t and time t plus delta t. So that means that the failure rate that we denote by lambda, the failure rate, which is in general a function of our current time, is equal to the limit value of the following expression. In this expression, we are considering the probability of the system failing between time t and t plus delta t, provided that the system was working at time t. Now this is what we call the conditional probability. That means it's the probability of the system to fail provided it was working at time lowercase t. Now for conditional probabilities we have this equation which should be well known from statistics. According to this hopefully well-known equation, the probability of A to happen provided that B happened is equal to the joint probability of both A and B happening divided by the probability of B. Now we can compare that to the equation that we have up here. The probability of B corresponds to this term that we have over here, and the probability of A and B happening, that means the probability of first having a case where the system is still operational at time lowercase t, and then the system failing until time lowercase t plus delta t. That is the change in the probability of the system still working. So that means using this equation we can rewrite the left-hand side into the expression that we see on the right-hand side. Down here R of t is what corresponds to the probability of B, and the nominator is what corresponds to the joint probability of A and B. That's the probability of initially the system being operational and then at time t plus delta t not being operational. Now obviously it's easy to compute the limit value of that expression because we just have to consider the case of delta t approaching 0. As a result, using well-known properties of mathematics, we come to the conclusion that this failure rate is equal to the probability density divided by the reliability. Now again, we can demonstrate these computations here for the exponential distribution. So we have to consider the probability density and divide this by the reliability. We do already know that these are the two functions describing these two parts of the left-hand side of this equation. And obviously, the result is a constant value of lambda. Now this is very interesting because this means that for the exponential distribution, the failure rate is constant. And that's actually a motivation why we have used that symbol over there as well, because in general the failure rate may vary over time. However, for the exponential distribution it is constant, and it is equal to this constant lambda. This in turn means that whenever we have a system where we can reasonably assume that the failure rate is constant, we can model that in a meaningful way using an exponential distribution. Now one question of course is the failure rate actually constant for real systems? Well, and there have been many cases where the people observing the failure rates have reported that the failure rates actually correspond to a so-called bathtub curve. That means initially we have a very high failure rate, which corresponds to so-called infant mortality. So due to infant mortality, we have these large amounts of failures. And then we have the stable situation where indeed the failure rate is constant. And then at the end of the lifetime of that product, the failure rate is increasing again. We have wear out, and due to the wear out, the failure rate is increasing again. So from this we can observe that the exponential distribution is an appropriate model for the second phase of the use of our product. The actual failure rate is typically measured in terms of so-called fit units, where fit stands for the expected number of failures in 10 to 9 hours. This fit actually needs some further mentioning because it is really used in many cases when people evaluate safety critical systems. There are quite a number of systems for which it is required that we achieve a failure rate of not more than 10 to the minus 9th per hour, and that would mean that for such a system we would be talking about one catastrophe on average per 100,000 systems, each running for 10,000 hours. There are cases where actually we would like to have a much better fit value, but on the other hand, there are cases where this is the key target. We cannot really go for 0 failures because that is not achievable in practice. So once again, FIT stands for failure in time. It's a failure in time unit for the failure rate, and 1 FIT corresponds to a rate of 10 to the minus 9 failures per hour. Now, in many contexts, it's important to consider the time for which we can expect to use a certain system. And this time is reflected by one term which is called MTTF. The MTTF is the statistical mean value of t. That means the amount of time after which, on the average, our system actually fails. And we are talking about averages there, so therefore we are computing this average like we are computing averages in general in statistics. This MTTF is just the expected value with respect to that probability distribution that we are working with, and we can also call this the first moment that we are considering. So we are not talking about second or third moments, it's the first moment. So for the exponential distribution, I can again show how we compute this statistical mean value there. What we do have to compute is shown on this part of the slide. We see that we have to solve this integral from 0 to infinity over a function where, in contrast to the previous equations, we now also have this additional factor of t. Now this integral can be solved rather easily if we remember the so-called product rule for integration. So this is the product rule for integration, where the u corresponds to the t, and the derivative of v corresponds to the second factor there. So according to the product rule, then, first of all, for the result, we have to put there u, which I told you is equivalent to t, so we put the t there, and then we have to put there the integral of v. So the integral of this part means that we will have, as part of the integration procedure, we will have minus lambda there and the denominator, so we can remove the 2 occurrences of lambda there, and as a result, the second factor will be e to the power of minus lambda t. Of course, there are these bounds 0 and infinity then. And then on top of that, we have this remaining integral corresponding to that part of the product rule. So there we have to consider the derivative of u. Now the derivative of t with respect to t is just a constant 1. And v, we already know, v is the same as what we have seen over here. So we just put there this function again. Now we can try to compute the integral. First of all, it's important to recognize that the first term is equal to 0. It's equal to 0 because for bound 0, the product obviously is equal to 0. And then if we are considering the case where t approaches infinity, it's obvious that this exponential decrease is a much faster decrease than the increase that we have there for the first factor. So therefore, as a result, the second term there also is 0. So therefore, we only have to consider this integral. We do already know how we integrate that function because we are just obtaining a contribution of minus lambda there in the denominator, so that's the contribution of minus 1 over lambda there, and we have to put there the original function, and we have to consider these boundaries. Then we can consider the boundaries, and if we insert the special values there, we are getting the result. The result is a value of 1 over lambda. Now that's a very interesting result, because that means that the MTTF for the case of the exponential distribution is the reciprocal value of the failure rate. That means, let's say, if we have, say, 100 hours until on the average we observe the first failure, then the mean failure rate is 1/100 in terms of hours. So that is what we are using in day-to-day life anyway, where more or less we are implicitly assuming a constant failure rate, and therefore this modeling by the exponential distribution is appropriate. Now, in the context of the mean time to failures, we can also introduce two other terms that are used in certain contexts as well. The first is the MTTR, which stands for the mean time to repair. In general, we can also consider a certain distribution that reflects the time that it takes to repair a broken system, and this is reflected, or the expected value for the time for a repair is reflected in the MTTR. And in addition, we can define the MTBF, which is the mean time between failures. The situation can be shown or is shown on this slide. You see that we assume that initially our system is operational, and then on the average it will be operational for MTTF time, and then it will be 40 for a time window that is reflected by this value of MTTR. And after that, we assume that the system will be operational again for a time modeled by MTTF. So obviously, the time MTBF, that's the time between failures, is equal to MTTF plus MTTR. Unfortunately, there are many cases where MTTF and MTBF are mixed up, because if you look, for example, at the specification of hard disk, you will frequently find values in terms of MTBF that are cited. This, strictly speaking, is totally wrong. Because if your hard disk breaks, you will just throw it. You never consider the repair. So therefore, talking about the time for a repair is totally useless in this context. But it doesn't really matter that much, because we assume that the time until the first failure is much, much larger than the time for repair. So therefore, being imprecise there is not that a big harm. But strictly speaking, it is actually wrong, and for hard disk we should specify the MTTF and not the MTBF. Okay, so considering a situation where we actually do repairs, we can consider for which percentage we actually have an operational system. And for this purpose, it does make sense to consider the so-called availability, which may be in general a function of time. Because if we have wear out, for example, this availability will decrease over time. So the availability is defined as the fraction of the system being available in relation to the overall time consisting of the sum of the MTTFs and the MTTRs. So that means, for example, if we have a system which is, say, 999 hours operational, and then you have to work for 1 hour on the repair, there we would have a value of 0.999. Now, the availability that is defined independently of time is actually the limiting value of this expression for t becoming close to infinity. That means we are considering a system that we are kind of using forever. We are considering the case where we are always repairing the system, and for this scenario we are then computing the availability. Okay, so this was the first introduction, a short introduction into the modeling of failure rates and the times until failures occur. Now, in practice, it's important to know what the order of magnitude we are talking about. How reliable are actually available circuits? Well, in general, it is very difficult to get some information there, because first of all, it's already difficult to compute these values. We are in a safety critical system talking about a situation where failures are rather rare events. So it could happen that we might have to wait for many years before we have the first failure, and then we don't have very dependable numerical results, because in statistics we would need to have large numbers, and having large numbers of failures for systems that keep working for many years is of course very time consuming. On top of that, in addition to problems with practically computing failure rates by using observations, many companies are not really interested in publishing their failure rates. Because consider a situation where one car manufacturer tells you that they achieve a reliability of 10 to the minus 9th hour, and another manufacturer has just half that value. So which car would you buy? You would possibly consider that value, even though it may hardly be relevant in practice, because compared to other hazards, the hazard of the car breaking because of some inherent problem is very low anyway. So therefore, it's very difficult to actually obtain actual failure rates. Therefore, I was very happy when I found this chart that tells us something about failure rates of actual devices. In this case, we are considering actual devices that are circuits made from gallium arsenide, which is a special semiconductor that's appropriate especially for very high-speed integrated circuits. And for this, the corresponding company is citing failure rates, and it is citing failure rates for very large amounts of hours. Actually, you can see from this chart that 135,000 hours are roughly corresponding to 20 years. So that means over here, somewhere over here, we have about 20 hours, and you see that this scale is a logarithmic scale, so we are talking about many hours there, and nobody would ever have time to actually run experiments that would take this amount of time. So you may wonder, how did the people arrive at these numbers anyway? These are experimental numbers. These are experimental numbers where people are using increased temperatures and then are using a known or assumed relation between the failure rate at a higher temperature and the failure rate at a lower temperature to predict the failure rates for these very long times. So assuming that these numbers are realistic, we can see that for these 20 hours, we are staying below a failure rate of 100 fit, which means that, well, the circuits are not failing, I would say, very frequently. However, we still have this failure rate of up to 100 fit. Now, I told you that in safety critical systems, we are targeting at failure rates in the order of not more than 1 fit. And we know that the circuits that we're using there have failure rates of up to 100 fit, which means that we are trying to design circuits, that we are trying to design systems that are more reliable than any of the circuits that we're using there. And obviously, this is only feasible if we use redundancy. Without redundancy, it's completely impossible to design systems that have failure rates in the order of 1 fit. Furthermore, and that's a second observation from the same chart, furthermore, it's very obvious that the assumption that failure rates are constant over time does not really apply, at least in this case, because this function is far from being constant. So it is anything but constant. Okay, so this gives you some information about failure rates that could be observed in practice. Now, when we do the analysis of failure rates of actual systems, we can use two different techniques. The first being called fault tree analysis, or FTA. In FTA, we are considering damages that are resulting from hazards or risk. And for every damage, for example, for a broken car, we have a certain severity and we have a certain probability. And there are several techniques that are used for analyzing risk. With FTA, we are using a top-down method for analyzing risk. Analysis starts with a possible damage and then tries to come up with possible scenarios that could lead to that damage. FTA typically uses a graphical representation of possible damages, including symbols for AND and OR gates. OR gates are used if a single event could result in a hazard, and AND gates are used when several events or conditions are required for that hazard to exist. So, for example, we can consider the case of having a hazard in an operating system. There are many possible reasons why we can have a hazard in the operating system, and for each of the reasons there must be several conditions that must be met for this hazard to exist. So, for example, if in a PC which is connected to the internet, we are not using a firewall, and there is an open TCP/IP port, and there is a bug in the operating system, then it can happen that we do have a hazard there in the operating system. And also, if the user receives email and the user clicks on the attachment and the attachment has a virus, then we can have a hazard there in the operating system. So with this very simple FTA technique, we do have certain limitations. These simple AND and OR gates cannot model all situations. So, for example, if we have some resource for which we have to measure certain amounts, certain quantities, then this would not work. For example, if we are considering the amount of power that's remaining in our system, then we cannot model this using these simple AND and OR gates. In such cases, Markov models may have to be used to model the remaining resources. The second example that is sometimes used for arguing about the reliability of a system is the so-called failure mode and effect analysis, or FMEA. FMEA works in the opposite direction, so therefore it starts at the component level and tries to estimate their reliability, and therefore the first step is then to consider the reliability of the component. So, for example, we could have such a table comprising an entry for a processor, where as a possible failure we are considering metal migration. Strictly speaking, there should be a fault here. So as a fault, we are considering metal migration, and as a consequence, we could have no service, and there could be a corresponding reliability. And of course, if we have metal migration there in the processor, we have a critical situation. So using tables like that one, we can compute the reliability of the system from the reliability of its parts using a bottom-up analysis. Now, both approaches, the bottom-up and the top-down approaches, may be used in safety cases. In such cases, an independent authority has to be convinced that a certain technical equipment is indeed safe. One of the commonly requested properties of the technical system is that no single failing component should potentially cause a catastrophe. So that means if, let's say, we have a train and a single wheel breaks, that should not result in a catastrophe. We know by experience that this requested property is not really easy to meet. For safety critical systems, we do in many cases have the requirement that allowed failure rates are in the order of 10 to the minus 9 per hour, which means that these failure rates are much less than typical failure rates of chips. So in this chart that I just showed, we had failure rates of 100 fit, but there may be other circuits for which the failure rate is even higher. So therefore, we know that the system as a whole must be more dependable than any of its parts, and that we have to use fault tolerance mechanisms. In this area, we do have a problem with actually testing whether or not we are achieving the goal, because we simply cannot wait long enough. So therefore, the actual safety must be shown by a combination of testing and reasoning. It's usually not completely feasible to demonstrate the targeted failure rates by means of testing. We must rely on a combination of arguments and testing. In the context of safety, it is very useful to consider advice by Hermann Koppitz, who has published 12 so-called design principles for safety critical systems. And I will briefly go through these 12 principles. According to the first principle, safety considerations have to be used as a part of the specification right from the beginning, driving the entire design process. It's not feasible to consider safety issues after we have generated a first design. The whole physical partitioning, etc., is affected by the need for going for a safety critical system. Then furthermore, precise specifications of design hypotheses must be made right at the beginning. These include expected failures and their probability. So for example, if we design a car, we must take into account that somebody could drive the car against a tree, and we have to consider the impact of such an incident. Then furthermore, we require to have so-called fault containment regions, and faults in one fault containment region should not affect faults in other fault containment regions. So for example, if we hit a tree with our car, the passenger compartment should still be stable, and this accident should affect only the front area there of the car, hopefully. Furthermore, according to the fourth principle, a consistent notion of time and state must be established. Otherwise, it will be impossible to differentiate between original and follow-up errors. In many cases, we have to be able to figure out what is the reason for having some incident, and therefore we must be able to know exactly at what time a certain event happened. Then furthermore, we must be using well-defined interfaces to hide the internals of components. When we design a car, for example, we are having a steering wheel, and we are hiding from the driver all the complicated actions that are involved with controlling the direction of the car. Then furthermore, we should ensure that components fail independently. So for example, we might have two different pipe systems there for the brakes in the car, and we should make sure that these two systems are definitely independent. Furthermore, according to the seventh principle, components should consider themselves to be correct unless two or more other components pretend the contrary to be true. That's the so-called principle of self-confidence. So if one of the brake systems is observing that the other brake system is behaving in a different way, it should still not give up unless we have a total of three such systems, and one system observes that the other two, or that the majority of the other systems, is taking a different decision. Then the one system might actually give up. Furthermore, fault-tolerant mechanisms must be designed so that they do not create any additional difficulty in explaining the behavior of the system. So that means that the users of the system should not have to bother with the impact of fault tolerance. Furthermore, the system should be designed for diagnosis. That means it must be possible to figure out what errors exist. These errors may be masked, so it may happen that these errors are not leading to failures. But we nevertheless must be able to figure out whether or not certain errors have occurred, and then we can possibly correct for the faults that have led to these errors. According to the 10th principle, the man-machine interface must be intuitive and forgiving. safety should be maintained despite mistakes being made by humans. According to the 11th principle, every anomaly should be recorded. These anomalies might be unobservable at the regular user interface, so therefore we should provide the means for recording these anomalies. Otherwise, it could happen that some fault-tolerant mechanisms is preventing a failure, preventing failures. And there could still be some underlying fault, and that of course needs to be discovered. And finally, these safety critical systems should provide a never give up strategy. That means even if the systems come to the conclusion that something is wrong, they should still not just shut down themselves, but they should try to provide functionality as long as possible by any means.